Welcome back, 216ers. This is Professor Kaufman, and what ensues is an overview video for Project 3. Only two problems to address in this project, but they are both a bit of a doozy, so prepare for somewhat of a challenge. The first problem deals with writing assembly code, and the second problem involves debugging it, and we'll get you accustomed to GDB in that setting. The topics are not particularly new in that the first problem, where you'll be writing assembly code, is identical in its domain to what you saw in Project 2, and that you'll be updating your thermoupdate.c file with a hand-rendered assembly version of this down there. And then if you enjoyed the puzzle box debugging exercise that was in C, puzzle bin should be up your alley as well. Perhaps not, though. It is a binary only distribution, which, similar to Project 2, has an input file that you'll need to progressively add more information into to pass the phases that are part of puzzle bin to earn more points. So try to deal with each of these in turn, but rest assured you'll be dealing with x86-64 assembly. And so if you haven't been tracking with the other course material right now and getting practice in lab on homework and lecture with assembly, this is likely to be an extremely difficult endeavor. And if this is your first time looking at assembly as you would look at this project, rather than getting practice in those other places ahead of time, start ramping up your attention very quickly, because you'll need to spend some time burning in on exactly how assembly looks in order to have any success on this. All right, let's start with problem one. It deals with the same three functions that you wrote in C before, this set temp from ports, set display from temp, and thermo updates, that are designed to create this thermometer simulator thing that reads from some global variables into a struct, and then uses that struct to construct a particular bit pattern that turns on lights so that a user of the pretend device would see a meaningful temperature in Celsius or Fahrenheit there. To that end, there's nothing new by way of same bit arrangements, same structs, and so forth. But dropping down to the assembly level is going to make this an interesting endeavor, as it'll expose all these things like, lots of the stuff that would happen in these functions doesn't happen in any data in the stack. It's instead uses registers to do the computations. As well, the handling of structs as they'd come in as a pointer or as a packed struct here, that'll be pertinent, and a recent lab has discussed those things, worthy of your review if you haven't looked at it yet. As you'd want to get set up or oriented on this, you may want to refer back to the original thermometer problem that came out of Project 2. And the same sorts of things apply here as apply there, that the eventual goal is to sort of create digit displays that look like this stuff, and possibly or the full displays of like minus 20 degrees Fahrenheit construct this bit pattern over here. So the simulator setup, as well as all the tests, they're more or less identical to what you were doing in Project 2. And so I won't belabor that power. What I will offer is a few advisements, pieces of advice, cautions as you start to work on assembly. There's a temptation here to let the compiler do the work for you, that in all likelihood you completed Project 2's thermoupdate.c and should know at this stage that GCC, as all compilers do, will generate an assembly version of that code as it's on its way down to producing an executable, a binary version. And if you know how to invoke the compiler, you can get it to spit out that .s file, and it's tempting to then just say, call it quits, let the compiler generate that for us. The staff are actually going to be on the lookout for this, because that subverts the point of the exercise, which is to practice coding assembly to get acquainted with those low-level structs, so that in the event that you're tasked later on to write at that level or write a compiler that would produce those kinds of instruction sequences, you've got a fighting chance to make progress on that. You'd completely miss the point of all of that exercise if you just let the compiler do it for you. Generally speaking, if we detect that you have automatically generated your code with the compiler, and there are a number of signs that we can be on the lookout for that, no credit will be given for manual inspection, and all automated test credit will be reduced to 0, because basically we've just resubmitted some version of your Project 2, some version of this. That said, it's extremely useful to have your copy of thermalupdate.c around as you completed Project 2. In particular, if you didn't finish the project, didn't finish this, or finished it in a dissatisfactory fashion, then you will potentially want to go visit a staff member in office hours, and they will help you to get up and running quickly. Part of this will be, we'll talk through what you struggled with in Project 2 on your C version of this, and then likely dispense a staff solution to this so that you have it on hand as a guide to how to construct your assembly code. This kind of thing can only be done during office hours with a TA, where you're talking in real time about it. But for those who are in doubt about their C version, this can be a good way to sort of get through that. Now, the things that are good signs that you're submitting a handcrafted version of your assembly code in this thermal update asm.s are as follows. You annotate your assembly code thoroughly. And this is not just for our benefit, it is for your benefit. The first dive into assembly means you're going to have to comment a lot of things in order to determine, just remember what's going on in there. So taking a largish function and subdividing into blocks, writing a little comment describing what each block is supposed to accomplish, commenting at various stages. These variables from my C program are stored in these registers, and describing some of the assembly instructions and their effects so that you don't forget them. These are all great ways to build an understanding, to get into the habit of sort of studying about this stuff, and to lock in this that kind of thing so that when it comes exam time, you're ready to write that stuff. You've been writing it and writing about it in your commentary there as well. One final note, the compiler is notorious for generating label names for jump targets as like .L1, .L2, .L3, so that's a dead giveaway. Any sane human is going to use more informative names for labels, points that they might jump to in their assembly code, like .rounding up for the spot in code where like, oh, I decided I need to round up. Or skipped rounding up as you would jump over some block of code that would increment on account of rounding. Those are nice for a reader. They're nice for you because they help you keep track of your code, and they're clear signs that you've been working on this and not letting GCC do your business for you. Finally, then, the use of the division instruction will be required at various spots. The easiest way to sort out, as we saw at Project 2, like, here's this 4-digit number, let me get the leftmost, middle two, and rightmost digits, use of division and modulo there. And so make use of the IDiv instruction, the assembly level version of division that computes a quotient and remainder. The compiler actually has a lot of tricks to avoid doing that. And in some cases, you should avoid those if you're dividing by a power of 2. However, when dividing by power of 10, like 10, don't do that. Instead, just bear the grunt of doing division, and that'll be a clear sign some human wrote this, and it wasn't the compiler using very crafty ways around division instructions there. One of the most common bits of student feedback as they've been working on this code is to comment the crap out of your assembly, as in write more in terms of commentary than you think. This will be important because if you work on this for multiple days, chances are you sleep on it and you'll lose some sort of memory of what's happening there. Other tricks, if you know how to block comment in your editor of choice, that's super useful. I'll sort of demonstrate that in my editor of choice. And also be careful about the use of bare numbers. There's a big difference between these two instructions. It is the use of the $ here, which makes the first instruction set the RAX register to 0. This one, second one is go fetch something from memory address 0 and plop it down in RAX. This will be a seg fault in most cases, so remember those. Lots of details to remember. There are register usage conventions, etc. And for your reference, the little picture that we talked about in lecture, the reference card for register usage is in here. As you're writing your assembly in the first pass, stick to these bluish registers. They're the so-called call save registers, which means as you're writing functions, you're free to change those without cost. If you run out of them and really think you need another register, then you might make use of the callee save registers at the expense of pushing and popping them. Now, there's some information about the structure of the assembly file, and we'll exploit that in mere moments as we sort of get into here. But you have to create this assembly file, this thermal update asm.s file. And so we'll do so shortly. It's a great idea then to take this template, sort of copied in, it has some hints and so forth in it that we'll survey in a second. But then it's a matter of filling in definitions for each of the functions. Some notes about each of them are present in the project specification, a reminder of what showed up in project 2, like the notes associated with that, but then also some additional information about the struct layout of the temp T struct that's used in this. So all you need at the C level is this bit of business, that it's a short and a character. At the assembly level, you need something that's a little bit more intense than that. And that table shows up down here. As you had been working on a lab where you're dealing with some coins, you need to know where are the nickels, where are the pennies, where are the dimes in the struct. So too, you'll need to know where those things are in the C structs here. So there are two modes of access for structs, again, through a pointer, as in C syntax like the arrow dereference, and the dot, which is a direct access to a present struct. As you're working in this first function, you should note it takes a pointer to a struct, and so you'll be doing some main memory references, and a guide to how to effectively access the fields are here. 10 degrees at a 2-byte offset, or sorry, 0-byte offset. It's a short, so it's 2 bytes big, so this would be an appropriate instruction to move 5 to that 10 degrees. And temp mode over here, if you wanted to move 5 to temp mode, it's at a 2-byte offset from where the struct starts, so that's 2 plus whatever register is pointing at the struct there, and this would move a single byte, so 1 byte quantity to that spot. Only 2 fields, so that makes things relatively easy. Finally, there are tips for this in the assembly code template that we'll copy in a second, but as well some discussion of it here. Accessing global variables in assembly is a little bit weird. To use the modern practices that we would typically want to generate position-independent code, things that we'll talk about in lecture moving forwards, you'll want to use the slightly strange syntax that appears here. There's a global variable named thermal sensor port. It's a 2-byte quantity, as in a short, and so move W is appropriate to access it. The syntax to use to grab that global variable's value and store it in the DX 16-bit register is to use the name for the global variable here, along with an offset from the instruction pointer, the RIP. Now this bears further explanation, which I'll get to in lecture. But rest assured that if you fail to use the syntax and just make use of the name here without a RIP offset, chances are likely that your code won't compile. You'll need to come back and sort of re-execute that. I think I've got things set up so that all students who fail to use the correct syntax will just get compiler errors. As in the past, we've had trouble where sometimes the Grace compiler, configured strangely as it is, will accept this, but then it'll fall down on Greatscope. I think I've got all the right flags in the makefile to set that up right. But if you fail to use the syntax, there may be penalties associated with it later, like your code doesn't run on Greatscope. So anyway, that should be enough to get us off the ground. Let's actually do just a little bit of coding here. So I'm going to scroll back up to the top here and grab the code pack. Copy that link address here. And if I change over here, I'm logged into Grace. I've got my little CMSC 216 directory, which I haven't worked in since Lab 1, so it's high time to add something here. I'll do a wget and grab that to download it. Do an ls. I've got my p3code.zip in here. So I'll unzip that, p3code.zip. Okay, I changed it here. So I'll have created the directory version of this. I'll change to p3 code here, and it should be good to go. Now out of the gate, if I try a make, I'm likely to get a build problem here, and that's there's no rule to build this part of it. That's the file thermal update asm.s that I need to create. Now, if you like, you can go grab your thermal update.c file from Project 2 and copy it in here, as you may be frequently referencing it. But that's not strictly necessary by here. Instead, our goal right now is just to get this thing up and running and run a test or two on it. So I can't run the test right now because I'm not actually able to produce an executable. I'm missing a file. So I'm going to fire up Emacs, my editor of choice. Configure just a little bit, interestingly here, but chances are likely yours won't look exactly like this. I need to create a new file, and Emacs, there's a mechanism for that. I just, find a file, then I'll call it thermo update asm.s. But If you're in VS Code, this would be create a new file. If you were gedit, like make a new file. When you save it, that's when you might choose this name. Like I'll pick it now, and save it later. Let's see. I get some error about line number mode not working out. We'll worry about that later. Now, the template for creating the assembly file, like it can be a bit intimidating to write yourself, but that's okay because midway through here, there's this section on the structure of this thing. And it's fine and dandy just to take this entire thing, copy it, and I think this syntax will work here, and paste it in. Yeah, okay. And I think I even got, all the indentation right. That's probably, some of it's a little bit messed up here. I'll probably move these back because I like the directives to be at the front over here, and maybe some of the indentation is like, not particularly great, but okay, so maybe good enough here. Now, this out of the gate won't compile. I'm going to open up a shell on the one of the windows here and type make again because the syntax that's used in here is a little bit wrong right now. And my goal for the moment is just to get this set up so that I can compile it. And the first thing that the compiler is griping about, let's see, I'm going to split this the other way so I can see that whole shell message here, is that there's no move X instruction. This is a demonstration line down here, and so it's not to be taken super seriously. It's a reminder again that the proper syntax to access a global variable is to use the global variable name and offset from the RIP address here and copy that into that register. But this is not a valid assembly line here, so I'm going to comment it out. I mentioned before a moment ago block commenting. This is a feature of most modern editors. The keystroke to do it in Emacs, doesn't pertain to like anything else. But generally, most editors have some ability to say, let me highlight some stuff and uncomment it or recomment it so that it is active or inactive. I think in VS Code, this is like Control/ or maybe Apple/ if you're on a Mac. And that will toggle comments on and off for a block of code. I can't remember. I know there's a way to do it in gedit, but it might actually involve like downloading an extension or something like that. And can't comment on the ability of the MOBA Xterm like built-in terminal to do things. But it's worthwhile to figure out how to do that, as it'll be a time saver. There's no block comment syntax in assembly like there's in C with the /* and then */. I don't even use that one very much because I'm so accustomed to my text editor being able to block comment things here. The final advisement is worth paying attention to here. The way code will run here in assembly is if I start executing this function, set temp from ports, it'll execute all the instructions right here. But if there's no return statement, it's just going to fall right into the next section here, which isn't actually executable code. It's data that we'll talk about in a minute. So I'm going to start my set temp from ports function out very simply just with a ret instruction. Now I haven't bothered to set a return value bot there. We'll get to that later on. So that will allow this function to run, and all it does is return, but at least it will run, and that will enable me to compile and run the automated tests that are provided. I'm going to open this up quick because I want to show a few more things in here. The assembly template provides a data section as well. This is where global variables can go. In fact, you can have these scattered around throughout the assembly file, but having one here is probably sufficient. None of these names are to be taken particularly seriously. They're there for demonstration purposes. For instance, this is a label called myInt, and it would allow later on code down here to say, oh, let me access myInt using the global variable syntax. Now, you don't have to do that for the global variables that are, you don't have to redeclare any global variables up here like that thermo display ports and thermo temp port, or things like that. Those things are declared and defined elsewhere. You can just make use of those names and see if you know what they are, as they're declared in C in assembly, if you know what those names are. But as you would need global variables yourself, for instance, an array of bit patterns, which may be very useful, then it's useful to like, oh, let me rename this and plop down a bunch of bit sequences here that are of interest. There are other ways to do this, but it's a nice rendition in assembly to do it. So folks generally recommend here for this project, lay out a global variable that's an array of bit patterns, even though maybe in your C version it was a local variable in this next set display from temp thing. But this is all fine in any code that declares single ints or an array of ints using the int directives over here. And so I'm not going to pay it any mind except to say that the data section means this is now read-write data, not executable. And so the directive down here will switch us back into text mode, as in this is executable stuff. To that end, I'm going to plop these things back over because this is the beginning of the second function. These instructions over here I don't really care about, as they demonstrate techniques to say get a value associated with the global variable or load the address of this global array into a register, which can be useful. But I just want to return at this point from this thing, so I'll pop down return. And then finally, it's a bit redundant to put a text here, but not going to hurt anything. This final function also needs a return. I'm going to save that here, and I think we should be good to go then. Now, I can't guarantee, but I'm pretty sure this should build at this point. Yeah, okay, so I type make, and that gives me my thermal main and as well the testing stuff, which we'll use in just a second. If I do a thermo main, this is making use of the assembly code for this. I need to provide, again, a sensor value and a C, so a C or an F. Let me just pick something like, was it 32? So if I did 3200 or 320, yeah, 320 should be 10 degrees above where the minimum temperature is. It doesn't matter right now because none of the functions in assembly do anything. So this set temp performance does absolutely nothing, as does the set display from temp and so forth. But importantly, I can also do a make test prob1 and run all tests, expect mainly failures here, but hey, the tests are running now, and that's an improvement over I can't even run the test because my code won't compile. No reason to let this sit around, so I'll press Control-C to stop this, and I can inspect the results later. But for now, I might want to start editing things in the assembly code. Let me come back over to that part, and it would be natural to start with this first function. So here it'd be a good idea to recollect, okay, this set temp from ports, the syntax in assembly here just says this is where to start, but I need to remember how does this function get information in the first place? To that end, it's worthwhile to look back over here at the C template for it, and information will come in here in this first parameter as temp-t over here. If you've been tracking at all at home, then you might look back at this register diagram to recall what was the register for the first argument? Oh, it's the DI family register. And this particular argument, it's a pointer, and so it will be a 64-bit value. It should be in RDI over here, RDI. And so this will be a memory address at which one would put stuff for this RDI for the struct. The fields of it, the tenths, degrees, and the mode are undefined, and so it's your job to generate some assembly instructions that will make use of this thing and at offsets, probably using instructions fairly close to what you see. Let's see where I have it down here for the tenths, degrees, and the temp mode and so forth, to move those to wherever the register points once you've figured out what the right values are for them. To get off the ground, it's not a bad idea to load up a global, the global variable that's passed in. This thermo sensor port. Oh yeah, it's not temperature or thermal sensor port. So I can probably just grab this assembly instruction here if I could get the whole thing. I move W into DX and maybe paste this thing down. This, if I believe the documentation, will copy the value of this global variable into the DX register over here. And just for giggles, let me, move L this R, or say EDX into EAX. So EX, as you look back at the diagram of special uses, is the return value. So all I'm going to do is load up this global variable and then return it as the return value from the function. That should give me just a little bit of sign that my assembly code is actually doing something, as I'll see it in the test. I only want to run maybe the first one here. Actually, I could run the main over here and see here. Thermal sensor port set to 320. That's there. And the result is returned here, and the result is 48. So let me see. 320 is a 48. That seems like a kind of a weird value to get there. I would expect like 320 to come back there. Let me think for a second about. Oh no, sorry, I'm looking at the wrong function here. Set temp from ports. The result that's returned from that is 37. 37 doesn't seem right either. Weird. Okay, not exactly sure what's happening with that part, but if I wanted to figure out, I could probably fire up the debugger here and step through this thing. So this is a good chance to do one of two things. I could fire up the debugger in the context of this thermal main here, and that would be something along the lines of GDB on this part, thermal main, and then set the args to be this thing, maybe break at my set temp from ports and so forth, and then go into TUI mode and that kind of thing. What I'd rather do quickly is to apprise you to one useful thing that you can do with the test cases, because it's more useful oftentimes to debug the test cases here. So let me run the first test case, and we'll see here that how to set up the debugger to run both those test cases in line, which can be helpful to step through your own code for it. So I want to run one of those. I'm going to make test prob 1. And I'll just do the first test number 1 over here. This will blast the stuff to the screen over here, but mainly what I want to see is, here's this big redonkulous return value, which doesn't make a ton of sense right now, because I thought it should be, moving this thermal sensor port into what should be returned here. It's minus 609,418,264. It seems like a strange value out there. Now we'll see that this is actually sort of sensible. One minor clue to this is if I run it again, I still get that same weird value over here. So up top, in terms of the top part of the test that most of the time students don't look at, but is extremely worth your while to look at. If you looked up here, you'd see, the reasons for failures are there were output differences and there were valgrid errors. As well, there might be some comments about it, but this line is extremely useful. It is what allows you to set up GDB to run an individual test and configure it to run just as you would for the testing framework is running. So I'm going to copy that line here and actually get into a normal terminal, because sometimes I have problems running GDB under Emacs here. If I paste that here, the only thing it's missing is the TUI part, but I can do that later. So I'll do a TUI enable. And then I want to break at my code. This was set temp from ports. And now if I give this a run, this will, after a screen refresh, stop right in my code. That's over here. I think if I move up one frame here, you'll see some things. If I move up another frame, I'll be in the main function over here, where I'm calling the set temp from ports thing. This is the context for that. To make things a little bit more reliable, I actually wrap the calls for set temp reports in a little assembly wrapper, but that's just to get sort of consistent results here. So I'm going to move the stack back down here to my thing. So ups and downs are useful in some contexts, maybe not this one. It's also worthwhile to see the backtrace here that's currently in this set temp from ports assembly file, which was called from this function, so semi-useful to know. But right now, what I'm mainly interested in is what's this code doing and wrong here? Why am I not getting an expected value of the thermal sensor port is apparently 0? Why am I not returning 0 here? It's not even the right thing to do, and I can't even get it right. So for that, I'm going to fire up the register file here. And if I step an instruction over here, I'll see sort of the registers come up. I'm interested in RDX here. And now that I see the registers, I want to sort of rerun to see how this thing plays out. Run from the beginning again. This breaks at the top of my set temp from ports. And one of the things that you might notice is like, oh, RDX up here has this weirdish value in it. Bad, 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 bad. It's like some professor said it to be that to apprise you to the fact that you shouldn't trust this value by going into it. Now, interestingly, doing this move W of thermal sensor port into RDX here, if I step an instruction, you'll see, let's see, after a refresh, it changes here. This part changes to zeros, and that's exactly what the instruction is supposed to do. Move 16 bits, 2 bytes to 8-bit quantities, that's these 4 hex digits up here, into the DX register. That's the low part of this RDX register. Grabs it out of global memory from this global variable and plops it down there. Unfortunately, this is a small move, a move W, which means the remainder of the register stays as it was. Bad, 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 as it were. In that respect, it wouldn't be a bad idea to add some code here that actually zeroes that register out. As I'm about to step an instruction forwards to change RAX, and you see, oh, now it has this really big positive value in it, and it doesn't look quite right in that regard. So let's make a change to that. So I'm going to suspend the debugger. Extremely useful tip if you're working in the terminal. The keystroke Control-Z will suspend one program. I've got a couple in the background right now, and I ask about this, what are the jobs that are on right now? I've got an old Emacs section, GDB there, a new Emacs session, this GDB over here. I want to get back to edit my code, and that was this Emacs call over here. It's job number 4. So I can foreground number 4 here. %4 is the shell syntax shorthand for that. And this will bring me back to Emacs. Right now I was looking at this shell output for the test result here. Let me change back over to my code here. And what we realize is that this is a small move, which only changes the low part of RDX. Let's just move a 0 into RDX here. That will zero it out. To see that effect, I'll need to compile again. So I'm going to change out of here and type make again. I think this will, update this thing over here. And then I can go back into my debug section. I forget the job numbers. Down here, this is Emacs I was doing, and here's GDB that was running on the test case. I'll foreground job number 5 in this case. That's this GDB1, which gets me back in here. Screen's a little messed up, no matter. And I will want to rerun from the beginning here. Oh shoot, had a board cord. No matter. I'll call that back up and rerun it here. Because sometimes when you change the executable, GDB gets like very upset about it. So that's okay. We didn't have a ton to do there. So break at set temp from ports, TUI enable, and then give this a run. This is break scenario. Now I see the code change that I had here. Let me set up my registers here. And then if I step an instruction, you'll see, RDX is now zeroed out. If I step another instruction, this moved a 0 into what's already a 0. And then I'll copy that 0 up here to RAX, and that'll be what returns over here. And so that's what's more or less going to happen by way of should see a sort of 0 return from this thing. Let's suspend that and then run the tests again. We'll make test prob 1, test num equals 1 here. Let's see if the output over here has changed at all. Still expect Valgrind problems, but hey, my test output, I'm returning 1 or 0 over here. It's probably worthwhile to maybe run the second one, test number 2 over here. Here, the thermal sensor port is set to 0, still returning 0. That's, kind of makes sense. And then if I did test number 3, this I think sets the sensor port. Let's see, the test sets the sensor port to 128, and I'm returning 128. Now again, this is wrong. The function is supposed to return 1 or 0 based on success or failure, looking for error conditions like the sensor port's out of range or something. But I can tell, hey, my assembly code is doing something. The next steps would be now that I've extracted this 128 and plopped it down in a register, I should probably do some arithmetic to convert it to a degree Celsius. That'll involve some shifting, some masking to check for rounding, possibly conversion to Fahrenheit. That'll involve checking this thermal status ports to see, like, oh, in this case, bit 5 is 0, so I shouldn't convert, but in some cases it'll be 1, so convert to Celsius, etc., and so on up there. The things that you did in C, like in assembly now. And finally, use that RDI pointer to write back to this spot in memory, but to overwrite the zeros here with whatever the actual temperature is. In this case, it would be negative 44.6 degrees Celsius, and the temp mode 1 for Celsius there. Okay, that's probably enough droning on this part of it, but hopefully you picked up a few techniques there. In particular, running an individual test case. The output for that is at the top of each test. So here I did it for this earlier test, but if the latest test that I just ran, number 3, I wanted to run that, I'd find the corresponding line up here, GDB with this set of stuff, and this will run the test code in the debugger so that you can hit an individual test case and look around at your code to see what it's doing. As well then for the terminal junkies out there, if you were doing things in the terminal, you can have several jobs open and switch between them, editor and GDB and so forth. Control Z to suspend many programs, and FG to bring one back into the foreground, as I did here for Emacs. Now that'll as well be useful as we start working on the next problem, this puzzle bin business. Let me change back over to the specs so we can jump down to that part over here. One final note on this. There certainly is partial credit awarded for this stuff. Just keep in mind that the last function thermal update is dependent on the previous functions working, and the main function is dependent on all of those functions working together. So to earn credit on the sort of later function, the earlier ones more or less have to work. There's 20 points associated with automated tests, 40 total tests at a half point a pop, and then various manual inspection criteria here, including the fact that passing all tests and getting all manual inspection credit includes in it 5 extra makeup credit points. So if you fail some tests, like no big deal, you can still get full credit. But if you're gunning to make up ground on past assignments, then this is a spot that you can earn a little bit of credit there. The second problem involves not writing code, but debugging code. What's been given to you is puzzle bin, and I may as well show it over here. If you do a listing, somewhere in there should be this puzzle bin. It's colored green here because it's an executable, and you can tell that by asking about it. L64-bit executable, it's statically linked, so it should run not just on Grace, but most systems. Gives it a few quirks, but that's easier for those running at home than forcing them onto Grace here. Your basic setup for this is going to be similar to the debugging exercise we just underwent with the, I guess several debugging exercises. It'll be useful, similar to the puzzle box exercise you did in the last assignment, but also you're going to be debugging assembly, and so what we just demonstrated with GDB is useful there. A typical cycle is as follows. You want to put the answers that you construct in this input.txt file. And then as you would want to use it, fire up the debugging session, set the args to be that, and then put it in assembly mode and have a look at the registers. Set a breakpoint at some phase where you want to stop, maybe, or where you're presently running. Just to get you oriented here, if I ran puzzle bin here, it'll say I need an input file. And to boot, if I hand it the default input.txt, it's going to complain right away. So part of the reason for that is that the input.txt, it has an invalid directory ID, and it's this should be your directory ID. In my case, I'm going to bop back to Emacs here and fire up that, find this input.txt. I'll use my old UMN handle over here for this thing. Now, I'm not even sure what the first phase needs for input, so I'm going to leave the 1, 2, 3 here for now. I'll suspend out of this, and now it's probably time to start the debugging session here. So GDB, TUI, and then this will be the puzzle bin here. You can see the TUI's enabled there. Maybe I'll do the registers first, and I'll set args to be the input.txt file, so that's red. If I just run this right now, and actually it's worthwhile to run it on the command line too. Here, if I do puzzle bin hub, you'll get the sort of expected behavior from the last project. Is like, oh, this first guess of 1, 2, 3 for the inputs isn't right, and so didn't even make it through this first phase of stuff. So 0 out of 40 points, and this can be a way to sort of track progress. If I ran this in the debugger, I get sort of the same output, which scuffs the screen and so forth, but I see the output down here. So I'll press Control-L to refresh that part. Clearly, I want to set some breakpoints here to poke around, but this is a rather intimidating factor up here. There's actually no source available for this. So if I break at main, that's fine, run, but there's no source available there for that. It's a good idea then to set this to a layout assembly, and here's where you can actually see instructions for main, because there's no hiding in the executable anything. It's got to be encoded in the bits that comprise the program. So the first few instructions are mains, are pushes and subtractions and some moves and some call of setup functions and so forth. That can't be hidden. It's not of great interest. If you scan down a ways here, you'll eventually find that after some setup, what's called is this phase 1, and that's probably where you'll want to devote most of your attention is into phase 1. Now, before we get too far and thick into this set of stuff, it's a good idea to recall that, well, this is nice to be able to look at the instructions for this thing. It's a bit limiting because I have to, scroll up and down here on this. And gosh, it'd be sure nice if I could get all this in some sort of text file without having to, copy and paste everything over and over again. And if you were tracking with lecture, you should understand that as there is an assembler, a program that converts textual versions of assembly to binary, there is also the ability to disassemble, to go in the opposite direction, to take this one-to-one correspondence between binary bits that encode instructions and convert them back to a textual rendition. So I'm going to plop out of my debugger for just a second here and remind there are commands listed in here. For instance, the object dump command. Where is that mentioned? Let's see, object dump. Yeah, down here. Now this is described in the quick guide to GDB, which also has tons of information about debugging assembly in this version over here, debugging assembly in GDB with the stuff here, as well as stuff down at the bottom that other tools that you might make use of. This is the one that's of a great interest right now. If you have something in binary, object dump-d will disassemble it. And so I just want to back up to get my spec back of the demonstration that is here. Here's object dump. So this is meant to work with binary executable files in the ELF format. -D is a shorthand for disassemble. And if I'm disassembling puzzle bin, then what will go onto the screen is a long stream of assembly instructions up here. And so scrolling aside here, all that stuff flashed by really fast. If you want that to go someplace meaningful, then I'd recommend redirecting that output from the screen into a file. This little caret or greater than sign here is shell syntax to say, take what would normally be printed and visible to the user and shuffle it into a file, which I'll name here. Here's puzzlebin code.txt or something like that. That might take a minute. But now, if I fire up Emacs, so I remember stuff. What is the Emacs is here? My 6th job. Probably got too many of these going up here. If I look around in here, there should be a new file, puzzlebin.code.txt. And this is the disassembly of the entirety of that ELF64 executable. Now, some of this stuff isn't of particular interest. It's like library functions that were inserted because it's a static. But if you search for main and sort of search around a little bit, you'll find the main function that we're looking at here. And the representation of these instructions should be pretty close to what you'd see in the debugger. Included in that is stuff like down here is a call to phase 1. And so this is where we're probably going to want to spend most of our time. And if you search for phase 01, somewhere around here, yeah, here are the instructions. Now, interestingly, this shows you the hex version of those instructions, as well as a textual version, so you probably pay more attention to this over here as you do things. I'm going to help you solve the first phase, but this is a nice part of that. You don't need to look at it always in the debugger, but you can look at phase 1, phase 2, this is a little longer, phase 3, longer yet, etc., phase 4, and potentially sort of poke around here to see other things of interest that might be in this disassembled file here. So I'm going to restrict my attention to what I can see in the debugger right now, but I'll leave all of you to sort of have a look as needed there. Let's see, if I figure out my jobs here, I wanted to do this puzzle bin, so that's foreground number 7 here. Let me get here. Now the first step in this endeavor is to try to figure out what does the first phase take in inputs. A quick hint, all of the phases themselves, they read their own inputs. So it's sufficient in most cases as you're working on phases to just break at like phase 01. And in this case, I'll continue, and that'll move until I reach another breakpoint here. And I set it at the beginning of phase 1, so here it is. This one's small enough it actually fits in one screen over here. And what you'll want to essentially be avoiding is any problems in terms of, oh shoot, that's layout assembly, let me refresh, and I need my registers. They're just, okay, so I can't actually see anything over here. But, well, shoot, I thought like somehow I managed to screw this up so that I can't actually like scroll my code around here, but no matter. But we'll step some instructions to sort of see what's happening there. So generally speaking, as you're working on this stuff, like you'll step some instructions, you'll see things change, etc. But your first step in each phase should be to figure out how it is, or what it is in terms of like what kind of stuff do you need to give it just in terms of input. Is it some numbers? If so, how many? Are they integers? Are they floating points? Is it letters or a full string? Like what is the input to this kind of stuff? Now a hint to that shows up here. There's a call. Oh shoot. Okay, I wanted to actually skip this part, so let me like rerun this from the beginning. I want to delete this first breakpoint because I don't want to stop at main anymore. I just want to stop in phase 1 going forwards. So there's a call here to a next instruction or next line, and this literally will read a line of input from your input file. And so as I would call that thing, you'll notice that RAX after the call instruction here, and I'll use NI because I don't want to actually go into that, it's immediately moved to RBX. As a result of calling next line, RAX is changed. This thing looks suspiciously like it might be some kind of a memory address. And so if you were to print it, for instance, print RAX, you'd see, okay, it's a value. It's this 50,232 thing up here. However, if you examined it instead, this says go to where this memory address points, this OX402FFF business, and show me what's there. Now, I have no idea like what's actually there, but on the suspicion that this reads a line of text, you might instead examine it not as a sort of hexadecimal number that's shown over here, but instead as a string. And at that point, this becomes, I get it. This actually did read the line of text out of my input file, which read 1, 2, 3, and it returned a pointer to it. And RAX, that's the return value from this function. It looks like I'm about to call another function here, and RAX is a caller save register, so it may be changed by PBRAND. And in fact, if it has a return value, RAX has to change on account of that. So that being the case, the compiler will have generated instructions that'll say, put this someplace that's safe across instruction or across call boundaries. RBX is a callee save register, so even if PBRand is going to change that, it will have to restore it. So we'll still have the pointer to that string after this call over here. Good things to know, but it's not crucial to our understanding yet part, because we're still just trying to figure out, is this 3 numbers? Is that what should I be giving this thing over here? So we'll step through over here, and ostensibly this thing gives some sort of an answer back. My point is that here is RBX over here. It's still this number over here, and if I were to go back and say examine not RAX but RBX, that input line is still there at 1, 2, 3. And so my input is safe across that there. Again, this isn't stuff that you'll necessarily have written. It's coming from the compiler, but it's good in terms of understanding what's happening there. Now, we might seek to sort of understand a few things about this, but it's not super necessary right now. And this is sort of hints to you about that. The main thing that was useful to look at is to look for where function calls are made that might compare things, or test instructions or comparison instructions that would lead to jumps away from other stuff. And so there's a call here to strcomp pb. And as a giveaway, this is just string compare. I wrapped it in another function because otherwise you get a weird sort of call site. It's hard to identify as a string compare. Now what you should look for then is something is about to get compared. It's getting set up in string comparison by plopping things that are going to be compared into argument registers. RDI is populated right before this, and lo and behold, it's copying RBX over here to RDI. RBX is where my original sort of string was stored, this 1, 2, 3. There's also something happening here with RSI. Maybe I'll go another instruction or two. Now I could try to do some mental arithmetic and severe sleuthing to sort of figure this out, or I could just execute this instruction as such and say RSI just changed. RSI is about to get passed to the string comparison. RSI is of interest, so let's have a look at it. Seeing as the thing it's going to be strcomped to is a string, it might stand to reason that RSI might also be a string. And so let's examine here as a string that's memory address that's stored in RSI. And lo and behold, there's something that looks semi-interesting over there. Now, if I step a couple more instructions, and actually next instructions, because I don't want to bother going into strcomp right now, move in over here, you'll find that RAX, as it returns from this strcomp business, it's a big, ugly looking number over here. And if I test that in the next instruction, and then jump not equal, I'll take that jump and get suspiciously close now to something that looks bad, like a failure part. So if I move to here and then sort of continue to completion, you'll see, this is where something went wrong, because those two strings were compared and they weren't the same. So the obvious conclusion to this is to figure out, what was that string one more time? Let me copy and paste it into the code that I have for that. Let me just try and resize that stuff to get the string taken there. Okay, so that'll be one more run here so that I can get sort of back into the right spot. I don't suppose, I got my scroll back over here. So in this case, what I really want is to stop right before this string comparison happens, so I can again look at RSI and RDI and so forth here. It's a handy syntax because you don't have functions or line numbers in assembly. Instead, you have instruction locations. So you can break at those using the syntax a star, and then something here, like I want to break at the instruction that is 55 bytes above where phase 1 starts. So I'll copy that and paste it down here. And this will set a breakpoint at a specific assembly instruction. In fact, whenever you would set a breakpoint on a line number in a source file, it actually has a correspondence in the debug information to this source line corresponds to this assembly instruction at this byte offset for film spot. And so what you're really doing when setting breakpoints is stop at this memory address as this instruction executes. But that'll allow me to continue. So I can just sort of fast forward to this spot, efficient debugging in that regard. And RDI and RSI are set up. So let me see here. Examine as a string RSI. This is that string: potatoes, boil them, mash them, put them in a stew. And then at RDI, this is my 1, 2, 3. So I want this thing to be this thing. I will do the copy paste pattern here. So copy this thing. Control Shift C on some keyboards to do this. Don't want to leave my debugging session. I just want to change my input. So let me zap out of this for a second. Let's see. In terms of jobs, I had opened up input.txt over here at Emacs. They foreground that thing here. This is not the code I was interested in. I wanted the input.txt, and I wanted this thing to be potato, put them in a stew. I think that looks about right. So I'll save that thing here. Press Control Z to suspend once more. And now just try running puzzlebin on input.txt. Hey, this is pretty good. Let's see. So phase 1 passed. Phase 2, there weren't any more inputs, but I passed phase 1 into phase 2, and I'm getting 5 out of 40 points. Let's come back to the debugger. So foreground that here of number 7. And I'll just refresh the screen, like this tearing is bad here. Now, I need to rerun the debugger to get the new input that I entered there. So I'll run again and say, yeah, go ahead and kill it. Started from the beginning. I'm going to continue to this point. So this should have read the new input from the input file. So let's examine as a string RSI. I think that was the one that was coming for this, but RDI is the one that I entered. So here, potatoes, mashed in the stew, so we're good to go on that front. They should match. So step and instruction. Oh, shoot. I didn't want to do that. I wanted to step over that string comparison to see what it returns. So I'll continue here. Okay, next instruction. And this is the primary difference. A step of an instruction will step into functions. So start going into the code for strcomp. A next instruction will say, just do this entire function and put me on the next line of code here. Tremendously useful if you don't really care about what code the strcomp is actually using there. So you'll see over here, RAX is a 0. And the typical convention for string comparison functions like this is there are 0 differences between those two strings. They match exactly. So that means on testing, I will get the jump on not equal, but in fact, the flags as they show up are over here. Let's see, on here, the 0 flags up, those two things are equal. So I'll go another instruction. I'm about to pop off that call esave register and return back up into main where I'm going to get some sweet points. So that concludes phase 1. Phase 2 starts out similarly, and at this point it's probably worthwhile to delete all the breakpoints and break phase 2 to say I'm done with phase 1. I may as well sort of continue on and run from there. So continue over here and start looking around. This phase, again, the first step is to figure out what exactly are the imports in terms of form. A good strategy on that is to provide an input line of some kind and then examine carefully the following call, which uses a scanf style function there. Examining the arguments that are associated with that to figure out what's getting passed into scanf here. That is extremely fruitful in this case to figuring out what kind of data should be fed to this phase. Whether it's a string, whether it's a number, whether it's a floating point value or some letters or something like that. All that can be determined by what is the format specifier that scanf takes in here. But I have gone on long enough about this. Worthwhile sort of follow-ups here. Each phase of the puzzle bin is worth a certain number of points, and you can get full credits essentially from completing not all, but some of the phases. Full credit is considered 40 points, but you can earn up to 50 by doing the normal phases. And if you look around really carefully, you may be able to find something else in there that could earn you an additional 10 makeup credit there. and that can be useful if you're trying to patch some gap in credits from a past project that didn't go so hot, or buttress yourself against future projects that might not go well. So I'll digress at this point and encourage you all to spend some time on this one, not to fret too much. Getting through the first few phases takes a bit of work, but will earn you points. And for those that are serious puzzlers, it will probably take you a little while to find all the little nuts and bolts that go into this one to earn that sort of maximum 60 over there. All right, that's enough for me. I wish you all happy hacking. Definitely spend a little time on this before spring break so you can get into the mood. It's not required that you code over spring break, but it's also a good way to do it at a leisurely pace if you're not otherwise occupied. I'll see you again in lecture soon. Happy hacking until then. Cheers.